Hi, I am going to explain the assignment 3. For design task part 1, U1 is an inverting amplifier, U2 is a summing amplifier, and U3 is a difference amplifier. So for U2, I rename this resistor to R3A, R3B, and R3C. So by derivation, the equation of Vout1 and Vout2 can be obtained. And also the final equation Vout3 is actually the difference between Vout1 and Vout2. So next, part 2 is to select a suitable value of the resistor. So for Vout2, according to part 1, this is the Vout2 equation, and this is the expected equation for the circuit design. So to determine the resistor value, the negative sign here can be ignored. So by selecting R4 to be 33 kilo ohm, the value of R3A, R3B, and R3C can be determined by the ratio. And this is the nearest value selected. So based on the similar approach, the value of R1 and R2 and also R5, R6 are determined. So the original functionality is to determine the difference between Vout1 and Vout2, but the part 1 design fails to produce it because the Vout2 obtained we have a negative sign. So therefore, an inverting amplifier with a unity gain is aided to invert the Vout2. So this is the simulation. And now you can see, now Vout2 will have a positive value. And this is the scope result. So this is Vout1 and this is Vout2, and this is the difference between Vout1 and Vout2 and multiplied by certain value. However, this simulation result cannot be replicated in the physical implementation because the power supply for the op-amp is only positive and negative 15 volt. But you can see the minimum value here is actually negative 20 volt, around negative 20 volt. So in the physical implementation, the op-amp cannot produce output exceed its power supply range. So in fact, it can only produce value slightly greater than negative 5 volt, maybe some value around here. So to preserve the original simulation output in the physical build, we should increase the magnitude of the voltage supply. Maybe we can use positive and negative 25 volt as the power supply. For design task 2, based on the input load, the load cell output different voltages. So this is the graph plotted, and the sensitivity can be calculated, which is the output full scale divided by the input full scale. And we will get 8.17 times 10 to the power of negative 5 volt per gram. And this is the signal conditioning circuit design, which will produce the voltage signal compatible with the DAQ system. So the sensor voltage, this is the sensor voltage, will be offsetted, should offsetted by a reference value, which I set it to be 1.53 volt, which is the voltage when no load input. Then the maximum load cell voltage is 1.579. So after offset, actually we will get 0.049 volt. So in order to have a voltage signal in range of 0 to 0.5 volt, the gain of the op-amp should be approximately 10. So we use a difference amplifier, and I select R1 to be 1 kilo ohm and R2 to be 10 kilo ohm to produce a gain of about 10 times. So now I run the simulation. As you can see now, the lot cell output voltage is now the maximum 1.579 volt, and by the signal conditioning circuit, you will get a voltage signal of 0.49 volt. So if I change it to the reference value, which are no input load, we should get a 0 volt. In addition, since the lot cell is actually a Whitson bridge constructed by only using resistors, so to eliminate the loading effect, a 1 mega ohm is added to increase the output impedance of the lot cell sensor. In other words, we increase the input impedance of this signal conditioning circuit. So after using a signal conditioning circuit, the lot cell voltage now will be compatible with the DAQ system now, and also we can recalculate the sensitivity, and now it increased by 10 times. It is 8.17 times 10 to the power of negative 4 volt per gram. So meaning a small change of the weight will lead to more obvious change of voltage.